Close your eyes for a second. Imagine a cavern, impossibly deep, miles beneath the rock beneath your feet. The ceiling stretches so far up you can't see it. The water below you glows, cold, ancient, blue. It has never touched sunlight. It has never been breathed. It has never been part of any ocean you've ever seen. That image is completely wrong. The real thing is so much stranger. There is an ocean down there. It holds more water than every surface ocean combined. But you could hold a piece of it in your hand, and it would look like a rock. That's not a metaphor. That's what scientists found in 2014, and it rewrote the story of all the water on this planet. You've been told Earth is the blue planet, 71% covered in water, unique in the solar system. But here's the question nobody asks. Where did all that water actually come from? For decades, the answer was asteroids. Icy rocks from the outer solar system crashed into early Earth. Billions of years of cosmic delivery service. That's the textbook version. But what if the water was always here? What if it was locked inside the planet itself? Deep, waiting, for billions of years. 700 kilometers down, in a layer called the transition zone, scientists found exactly that. Water, not liquid, not frozen, something weirder, trapped inside the atoms of a blue mineral called Ringwoodite. And when they calculated how much was down there, the number was staggering, potentially more than all our oceans put together. This is the story of that discovery, and why it changes almost everything. It started in a riverbed in Brazil. 2008. A group of miners in the Huina region of Mato Grosso pull a small brown diamond from the gravel. It's ugly, worthless on the market. $20 if that, they sell it. Nobody notices. A few years later, that diamond ends up with Graham Pearson. He's a geochemist at the University of Alberta. He's not looking for treasure. He's looking for information. Inside the diamond, almost invisible, he finds an inclusion, 40 microns across. That's less than half the width of a single human hair. His team runs it through every test they have. X-ray diffraction, Raman spectroscopy, infrared analysis, and what they find has never been seen before, not once, not anywhere on Earth. Ringwoodite, a mineral that scientists knew existed only in meteorites and in lab experiments. Never here, never from inside our own planet. Water changes everything about the way a planet works. That's what Graham Pearson said when they published, and that's exactly what they found inside the Ringwoodite. Water, 1.5% of the mineral's total weight, from 500 kilometers below the ground. But there was still a question. Was this one weird rock, a local anomaly? Enter Stephen Jacobson and Brandon Schmant, Northwestern University, University of New Mexico. They were studying earthquakes, not diamonds. They used nearly 2,000 seismometers spread across North America. They analyzed the shock waves from over 500 earthquakes. Seismic waves travel at different speeds through different materials. And at 660 kilometers deep, they were behaving strangely, slowing, scattering, like waves hitting something wet. Jacobson found melting rock at 660 kilometers depth. Melting caused by water from inside the minerals themselves. This wasn't a local accident. This was a whole layer of the planet quietly soaked through. To understand this, you need to know one mineral. Olivine. It makes up most of Earth's upper mantle. It's everywhere down there. But olivine is not fixed. Under pressure, enormous, crushing pressure, it transforms. Its crystal structure reshapes entirely. At 410 kilometers down, olivine becomes Wadsleyite. At 520 kilometers, it becomes Ringwoodite. a blue, spinel-structured mineral. And here's the key thing about ringwoodite structure. It has gaps, tiny pockets in the lattice, and those pockets attract hydrogen. At 17 gigapascals of pressure, that's 170,000 times the pressure at sea level, a water molecule gets split. The hydrogen atoms get absorbed into the crystal. They bond with oxygen already there as hydroxyl ions, OH-. Water doesn't exist as liquid. It doesn't exist as ice. It exists as part of the rock itself. This is why Jacobson called it sweating. Push ringwoodite back to the surface. Reduce the pressure, and it releases the water. Liquid, instantly. Now, picture this at scale. The transition zone runs from 410 to 660 kilometers deep, a layer of ringwoodite roughly the size of a continent. If just 1% of its weight is water, that's 3 times the volume of every ocean on Earth's surface. 3 times. Sitting silently inside the rock, right now, as you watch this. So, how did it get there? It didn't teleport from space. It was dragged down by the same force that moves continents. At subduction zones, oceanic plates dive beneath continental ones. They carry water with them. Water locked into minerals, serpentine, chlorite, amphiboly. Most of that water gets squeezed out at 30 to 150 kilometers depth. It triggers volcanoes. It rises back up, but some survives. The deepest, coldest parts of the slab, the peridotite mantle, can carry water past 300 kilometers, past 410 kilometers, into the transition zone. There, the minerals change, and the water gets locked in. Permanently, crystallized, trapped. This process has been running for billions of years. At modern subduction rates, it takes about 80 million years to cycle the entire mass of Earth's oceans through the mantle once. Over 4.5 billion years. Scientists estimate 2 to 3 ocean masses may have been pulled underground. And here's the haunting part. More water is going in than coming back out. Earth is slowly, very slowly, drying. Sea levels may have dropped 130 meters just in the last 200 million years. Partly because of this. The ocean isn't disappearing fast, but it is disappearing. This discovery tears open one of science's oldest questions. Where did Earth's water come from? The comet theory, water delivered from space, looks incomplete now. Even the Rosetta mission found that comet water doesn't match our ocean chemistry. Asteroids are a better fit, but they only explain some of it. Now, there's a third option. Earth may have made its own water. Hydrogen, baked into the rock during planetary formation. Slowly released over billions of years. As the 2014 Nature paper put it, the ultimate origin of water in Earth's hydrosphere is in the deep Earth, the mantle. This changes everything about how we think planets work. If rocky planets can generate their own water from the inside out, that means oceans might not require a lucky asteroid strike. They might be common, built in. It also explains why Earth's oceans haven't dried up or overflowed. The transition zone acts like a planetary thermostat for water. Too much on the surface, more gets subducted. Too little, less goes down, more comes up through volcanoes, a self-regulating buffer. That has kept liquid water stable on this planet for hundreds of millions of years. Stable enough for life. And then there's the volcanism connection. At the 660-kilometer boundary, ringwoodite breaks down. It releases water into surrounding rock. Water lowers the melting point. Rock melts. Melt rises. Some of the magma you see erupting today has been on a billion-year journey from the deep water cycle. You look at a volcano and you think it's fire. It's also water. Here's what gets me about this whole story. The most important geological discovery in decades was hiding inside a rock worth less than a cup of coffee. A misshapen brown diamond, pulled from a Brazilian riverbed, sold for $20. It took years of painstaking work to see it. A 40-micron speck, less than half the width of a human hair. The first piece of Earth's own mantle transition zone ever held in human hands. And it was wet. When we look at this planet, this blue marble, we've always assumed the water was on top, sitting on a dry rock. But the rock isn't dry, it never was. The ocean you can't see is bigger than the ocean you can, and it's been there since before the first cell divided, before the first fish swam, before the first human looked up at the sky and wondered. The universe didn't just deliver water to Earth. Earth was born holding it. We live on a water planet. We always thought the water was up here with us. Turns out, we're the ones on top. Next time, what happens when all that mantle water finally comes back up? The answer involves a supervolcano, a missing ocean, and the end of the world. Subscribe, because we're just getting started.